Record. Recording's rolling. Wednesday, October 1st. So, got a Kahoot up. A lot of you guys are logged into that. So, the third law of motion. Guys, Newton's third law, is that the equal and opposite rule? Yeah. Okay, so, let me pull that up real fast. That's the one that goes, it's right here. Okay. So, for every active force on object A by object B, there's a reactive force equal in magnitude opposite direction by object B back on object A. I have a couple of examples here. Okay? So anytime you have two interacting objects, they're pushing or pulling on each other, the forces are always equal and opposite. Even if the masses are different, the resulting accelerations could totally be different. That could expect to do second law motion, but the forces are always equal and opposite. So let's see how well you guys do on a set of Kahoot questions. We're going to find out. Uh, Yesterday we did a different Kahoot. We had about 10 or 15 minutes at the end of class to solve technical puzzles, so probably about the same routine today. Do as much as we can. Whatever we do in class, that's just what we do on Friday. So as long as you're following along with the puzzles, I'll pick those up from you guys on Friday. And then I was going to get you a quiz by the end of the week. Now, for a number of reasons, yeah, including my other type physics class. Here, I'll end up putting this quiz in your hands by the end of the class, and then we'll just make this another take-home quiz, and you guys can turn this in by Monday, which is like plenty of time. Okay? Because the next 2 days, I wanted to finish off this week with some lab type activities. One lab type activity I want to do with you guys is where you guys put your spring scales, and you guys figure out what's the spring constant in all these each scale. Like this green one has a tiny force to stretch it from distance. You guys see that? It's really easy to stretch it. But like this gold one is like the opposite. This gold one like huge force. It's really hard to stretch this one. So how can I quantify how stiff are these springs? Okay. Some number of newtons of force it takes to stretch it some distance that maybe could be in meters. Let's see, newtons per meter. I can quantify it. And the other activity I want to do with you guys by the end of the week is called Virinon frame. This is one here. So quick intro to this. Let you guys think about this one overnight. This is a physics solution to a business economics type problem where what if you want to build a factory? Maybe you have some different inputs, maybe lumber from this forest or copper from this mine. Right? You put it all together, and then maybe some kind of output product that you want to ship to this town. But maybe every one of these has some different transportation costs. Maybe it's really expensive for one of these and kind of cheaper for to transport another. Okay? So, guys, where would you put your factory? Would you put it let's say it's like really expensive to transport the final product for some reason, for whatever reason. Okay. Do you want to put your factory really close to the town or really far away from town if it's really expensive for this leg of the trip? Really close to the town? Probably really close. That would make sense, right? In terms of physics, all you have to do is where the town is, put a large weight, and the weight would be directly proportional to the corresponding transportation cost. And this will set up a natural equilibrium. It'll tell you exactly where to put the factory. Yeah, so you guys get to do that before the weekend. All right, but today main activity is Kahoot. Oh, look at you guys go. We are ready for Newton's third law of motion. 20 questions. I'm only about two though. Whenever an object exerts a force on another object, the second object exerts a force same magnitude in the opposite direction to that on the first object. Is that always true? Or is it only sometimes true? Is it always false? Wait a second. Yeah, that's what I showed you guys. Guys, that is Newton's third law stated. That's Newton's third law. Right? Actually, every single question in this Kahoot is going to be somehow related to that statement, isn't it? Right? Guys, how about this? Is the Earth pulling on the moon? Yeah, it's giving it an Earth orbit. Is the moon pulling back on the Earth? Yeah, okay, but which force is bigger? Yeah, same force. It's the same force. Same force. Right? Is the Earth pulling you down, holding you in your seat? Are you also pulling up on the Earth? Yeah. Okay, but which force is bigger? It's the same force. Same force. Yeah. All right. I got points on the board. Points. Ready to go. High school student hits a nail with a hammer. Now, guys, if you're hitting the nail with a hammer, which way is the force? Hitting the nail with a hammer. Yeah. There's a force down on the nail. There's a reactive force back on the hammer. Right? Because which force is bigger? They're equal. Yeah, they're equal. Same force. Same force. Yeah. Maybe that's why I should have phrased that question. I got Talia, Cole, Kai, Dara, Anna. Ooh. Archer shoots an arrow. Consider the action force to be the bowstring pushing the arrow. What's the reaction force? See, the bowstring's pushing against the arrow. The reaction is the yeah, the arrow pushes back on the bowstring. Right? Now, there's maybe these other forces might also be applicable. They just wouldn't be the third law equal and opposite force. Right? Speaking of which, guys, which force is bigger? The bowstring pushing on the arrow pushing back on the bowstring. That's the same force. Same force. I got Talia, Dara, Kai, Gavin, Anna. Player catches a ball. Consider the action force to be the impact of the ball against the player's glove. What's the reaction? So the ball hits the glove. The reaction is the glove slowing down the ball, right? Yeah. Glove hits ball. Or, yeah. Ball hits glove. Right? Equal opposite. In fact, there's definitely a force on the ball because it changes its motion, doesn't it? It slows it down from full speed to zero. Talia, Kai, Dara, Gavin, Anna. Dara's on fire. Player hits a ball with a bat. The action force is the bat against the ball. What's the reaction force? Yeah, the ball against the bat. Against ball against bat. Okay. Here, let's follow up here. Let's say the pitcher throws the ball, and the throwing speed is like 30 meters per second. Yeah. And then the bat, like bam, and hits back the other way at like 50 meters per second. Okay, bam. So it's coming at the bat at 30 meters per second, and bam, hits it back the other way, 50 meters per second. Okay. In that case, during that collision, which force is bigger? The ball hitting the bat or the bat hitting the ball? The bat hitting the ball. They're the same. The same force. It's the same force. That's Newton's third law. It's the same force. Bat on ball, ball on bat, same force. Yeah. We got Samuel, Talia, Gavin, Dara, Anna. Ball falls. Let's say the action force is the Earth's mass pulling on the ball. What's the reaction force? Let's see, Earth pulls down on the ball. Yeah, the ball pulls up on the Earth. All right, there you go. All right. All right, got Cole, Talia, Gavin, Deborah, Anna. Unfortunate bug splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is what? That's the same force, right? Now it might be a small force because the bug is really small, maybe only like a couple of grams, so there's not a lot of force to go around, right? Okay. But from the car's point of view, like that splat, it doesn't really slow down the car very much, does it? Hence, it would also be a small force. So we are talking about a small force, right? Now, a small force on a small bug is going to splatter the bug. Small force on the car, okay. And that actually connects to the next question. We got Cole, Talia, Gavin, Dara, Anna. Okay, exact same scenario. Different question compared to the deceleration of the car. Let's call it the change in motion of the bug. Right, so the change in motion of the car, the change in motion of the bug is what? of a different question. Much, much larger, much larger. Okay, so the forces are the same. So the forces are the same. But what you guys just got is actually a second law question. You guys remember this right here? Okay. It's the same force on different masses. We'll draw this one out too. So we got uh, here's car. Oh, car with right. And here's your bug. Right. So right. Now, guys, what if the bug was just like flying around? Let's say it's relatively stationary. Right? Just like, oh, what a nice day. It's not really moving. And then the car starts to pow. And now, aren't they moving together at about 60 miles an hour? Maybe 60 miles an hour? Right? So the change in velocity of the bug went from 0 to 60, wouldn't that be like 60 miles per hour? Right? But the change in velocity of the car, it doesn't change that at all. Yeah, the amount of changes would be negligible, right? If I go from like 60.00001 to 60, right, so it might be closer to, or I'll say approximately 0.001 miles per hour, right? It'd be so small that if you were inside the car, you wouldn't even notice. Right, guys? And that's the physics that backs that up is actually Newton's second law of motion. So it's the same force on the bug in the car, but the bug is maybe just a few grams. So that's a huge acceleration. That's a huge rate change in velocity, something related to this. Okay? But for the car is like thousands of kilograms maybe. Okay? So a little tiny force of a few newtons, it causes almost zero acceleration. Okay, so guys, what about this? What if there's like a million bugs? They're all like, this is flying like a million bugs. This car's plowing through like okay, maybe the car could slow down from like 60 to 59 miles an hour, maybe. Okay, maybe you start to fill it up at some point. Okay, just a little increments. All right, you guys got that? I got Cole, Gavin, Talia, Dara, Anna. Horse pulls a wagon at rest. The wagon pulls back equally on the horse. Can the wagon actually be set into motion? Oh, sorry, I didn't notice it would be so small. Red, yes, because there's a net force acting on the wagon. Blue, yes, because there's a time delay between the action and reaction. Yellow, yes, because the horse's pull on wagon is larger than wagon's pull. Or green, no, because the forces cancel each other out. Yeah, right. There's a net force on the wagon, is what I'm looking for. Right, there's a net force on the wagon. Right, so I should draw that one out too. Right. This is the textbook that I got this from. It's actually Paul Hewitt's textbook. That's where these Kahoot questions, most of them come from. Right. Yeah, there's a whole page he has about just related to this question. Like, what if you had like some wagon? Right, it's got like a wagon. I made that too big. Let me try it again. Sorry. Okay, got like little wagon wheels. Okay, wagon. Okay, there's like a horse here. Or whatever. I guess I got an elephant looking horse there. Okay. And then pull up. Okay, so what are the forces here? Now the tension in this rope. Here, guys. There. Is there a tension in this rope that's pulling the wagon forward? Is this tension also pulling back on the horse? The horse feels the tension pulling back. Okay. Guys, which force is bigger? The tension pulling the wagon forward or the tension pulling the horse back? It's the same tension. It's the same tension either way. Guys, there's only one tension, and maybe this rope right here. It's the same tension. Okay. Now, so why can't this be set into motion? Right. This whole system, the horse cart system, because it would be set into motion, wouldn't it? Okay. So if I throw the ground right here, you swim by the ground. Okay. Now, from the wagon's point of view, the wagon, here I'll do a free body diagram, has a weight. There's a weight of the wagon. There's a normal force holding the wagon up, and there's a tension force pulling. I'll do F sub T, tension force pulling the wagon forward. Okay. Maybe tiny frictional forces, but those are the main forces that matter, right? Yeah. Now, from the horse's point of view, they have a little longer legs, so it can reach the ground. Covered. From the horse's point of view, what we got? There's definitely the tension pulling back, and it's the same force, guys. It's the same force. Okay? Maybe the horse has its own weight. The horse has its own normal force. Okay. But guys, as the horse has its feet planted in the ground, it's like moving forward. There's one more force I haven't drawn yet. And it's what force? I'll give you a hint. if this was iced over, it'd be really hard to make this move at all. Friction. Ah, friction. Yeah. Okay. And since the horse's feet are like moving backward relative to the horse, that friction would be pushing forward. So there's a friction force. Friction force is actually what allows this whole system to move. Okay. And this would be the net force on the entire system, the horse cart system that actually lets it start moving. Right? Same thing with your car. Right? If I replace this whole horse cart system, well, what makes your car move? Because if your car's like parked in the mud, like a big old mud pit, you put it in drive and press on the gas pedal, don't the wheels like ooh, to spin in place and it doesn't move at all? Right? Well, what if you have solid ground like asphalt right here? Okay. Here's the actual free body diagram. So your car has a weight, your car has a normal force holding it up, okay. And then these wheels spinning. Yeah, it's actually the friction force between the tires and the road that allows the car to take off and start driving. Yeah, that's the actual driving force. All right. Okay. Here. I got Olivia, Cole, Talia, Dara, Anna. Question two. A large truck and a small car traveling at the same speed have a head-on collision. The vehicle to undergo the greater change in velocity. Well, change up question at the end there. Change in velocity. It's a small car. Yeah. This is the sort of the same thing as the bug versus the car, but maybe not as extreme. Yeah. Okay. You guys, which force is bigger? The force on the big car or the force on the small car? Same force. Okay, so it's the same force, but on different masses. So the smaller mass receives the larger acceleration. Right? That's it. That's actually Newton's second law, isn't it? That's a second law question right there. Right, so the small car, yeah, undergoes greater change in motion. Got Cole, Gavin, Spencer, on fire. Dara, Anna. According to Newton's third law, if you push gently on something, it will push. Gently back on you. Oh yeah. Oh yeah. So action, reaction. There's a Newton's third law pair. Cole, Gavin, Spencer, Dara, Anna. Earth pulls on the moon. Similarly, the moon pulls on the Earth. This is evidence that, see, the Earth and the moon are pulling on each other. The Earth and moon's pull comprise an action-reaction pair. Both of the above, none of the above. Yeah, so both of the above. Right. Actually, the moon orbiting around the Earth. So that gets into like circular motion and orbital mechanics, which we haven't talked about yet, but we'll probably which is coming real soon. Probably next week. I think we'll start talking about orbital mechanics. Got Cole, Spencer, Gavin, Dara, Anna. Nellie Newton holds an apple in her hand. If the action force is Earth pulling down on the apple, what's the reaction? Is it her hand providing a normal force? Her hand pushing up the apple? Both of the above? None of the above. Yeah. So if the Earth is pulling down the apple, what's the reaction force? The apple pulling up on the Earth. Yeah. Earth pulls apple down, apple pulls the Earth up. Right. But which force is bigger? The same force. It's the same force. Same force. Spencer, Cole, Gavin, Dara, Anna. Bronco the skydiver falls toward Earth. The attraction force is Earth pulling down on Bronco. What's the reaction force? Is it the air drag on Bronco? Bronco pulling up on Earth? Earth's surface finally pushing against Bronco when he lands? None of the above. Yeah, Bronco pulls up on the Earth. Right? So Earth pulls down on Bronco, Bronco pulls up on the Earth. Right? Now, nobody picked the air drag, which would be a common like decoy answer, right? Because there could be air drag, right? Guys, is there air drag maybe pushing up on Bronco? Yeah. But the reaction force to that is actually Bronco pushing down on the air, which is different than Bronco versus the Earth. Yeah, it's a different action-reaction pair. All right, got Gavin, Spencer, Cole, Dara, Anna. A force is exerted on the tires of a car to accelerate the car along a road. This force is exerted by the what object external to the car is actually pushing on the car, allowing the car to move. It's the force from the oh yeah, look at you guys. Yeah. So the best answer is the road. Yeah. So there's a friction force between the tires and the road. The reason the road is a better answer is because the tires are internal to the car. So yeah, so the external object providing the external force would be the road. Yeah. All right. Pretty good. Oh, sorry. Rocket is able to accelerate in the vacuum of space when it fires its engines. The force that propels the rocket is it the force of the exhaust gas on the rocket or the force of the rocket on the exhaust gases? What's propelling the rocket forward? Okay, I'm sure they gave you guys more time. Okay, good. Now that is an action reaction pair, right? So the rocket's pushing down on the gases, and the gases are pushing up on the rocket. Is that true? Okay, but guys, which force is bigger though? Same force. Same force. Gavin, Cole, Spencer, Dara, Anna. Karate chop, blow 1900 newtons onto a board that breaks. The force that acts on the hand. Ooh. So the force from the hand on the board is 1900 newtons. But the force back on the hand. Everybody's winning. Oh, yeah. 1900 newtons. Got Gian, Cole, Spencer, Dara, Anna. Woman weighs 450 newtons, sits on the floor. She exerts a force on the floor of. Okay. Yeah, also 450 newtons. Right. Now, there's two different action reaction pairs going on here. Right. There's her versus the Earth. That's 450, 450, equal and opposite. And there's also her versus the floor, which is a different action reaction, but the numbers are the same. Okay. Okay. Now, that would be different. Guys, what about this? What if the floor was actually an elevator and the whole elevator was accelerating upward? Then would that the force from the floor would be different, wouldn't it? Okay. But so would her force pushing down on the floor. Again, if it was like an elevator that was accelerating, okay. It would still be an action reaction pair, and the forces would still be equal and opposite. Okay. Here, I'm going to draw out what I just said because I hope that wasn't confusing what I just said. Okay. So if she's sitting on a floor at rest, need wallpaper. Okay. If she's sitting on a floor at rest. Here, I'll just how we're standing. That's easier, right? So stand here. Then, say she weighs 450 newtons. Okay. Now, if I do a free body diagram on her, then there's a normal force from the floor that's 450 newtons. Okay. But this actually is not the action reaction pair, although it looks like it, but it actually isn't. Because these are the forces only on her. Right? Whenever I have you guys draw a free body diagram, we're only focused on a single object. Action reaction pair, I have to consider everything else that's going on. So the reaction force to her normal force is pushing down on the floor 450 newtons, which is the answer you guys have. Okay. The reaction force to the Earth pulling down 450 newtons, so she's pulling up the entire Earth. So if the center of the Earth was down here, pulling up 450 newtons would be the equal opposite of this one. Right? Now, if she steps in an elevator, and let's say she's standing on a scale. Standing on a scale in an elevator. Okay. The whole elevator is accelerating upward. I'll do A for acceleration. Okay. Then in that case, suppose the Earth's still pulling down with 450 newtons weight, so that's her weight. Okay. Guys, could this scale and the whole floor be pushing up more than 450 newtons? Could be, for example, like 500 newtons. Could that be okay? Okay. Hey, hang on a minute. I drew different forces. Does that break Newton's third law? No, because, guys, what's the equal and opposite to the Earth pulling her down? Yeah, she's pulling up on the entire Earth. So if you had the center of the Earth and pulling up, this would be 450 newtons. Okay. And from the scale's point of view, the scale's pushing up on her at 500 newtons. But guess what force she's actually pushing down on the scale? And it's not 450. It's 500. She's actually pushing down on the scale with 500 newtons worth of weight. Yeah, so that would be the equal and opposite. So if I did from the scale's point of view, there would be down force of 500. Yeah. Okay, so there's different objects going on there. Right, there's her, there's the scale, for the floor. There's the earth. Right. Weighs 450 newtons, sits on the floor. The floor exerts a force back up on her. Everything's just at rest. Um, um, all right, 450 newtons. Right, so equilibrium. Talia, Gian, Cole, Spencer, fire, Emma. And for the win, two people pull on a rope in a tug of war. Each person pulls with 600 newtons. What is the tension in the rope? Hmm. Think about that one. So you did here. Oh, hey, yeah. Most you guys got that. All right, well, the plurality, or no, yeah, half of you guys got it. Yeah, 600 newtons. Yeah, so if everybody's pulling with 600 newtons, yeah, it turns out the tension in the rope would be 600 newtons. Actually, for something like this, I normally draw pivotal scenarios. So the way the question was framed, I'll go to the podium too, and we'll see who won Kahoot. Right. It's like if this person pulls to the left with 600, this person pulls to the right with 600 newtons. Okay. The tension would be 600 newtons. Oh, guys, what about this? What if I cut open the rope right here and I slip in one of these spring scales right here? These spring scales. Okay. What is the spring scale read? 600. Right, guys, 600. Okay. And what about this? If nobody's moving and they're just like pulling, and the rope's just really taut. Okay. Guess what is the force of friction between their feet and the ground? Yeah, 600 newtons. So 600 here, 600 here, 600, 600, right, 600, 600. What if I replace one person with a tree? Okay. And same thing. Let's throw a little spring scale in here. Little spring scale. Okay. And then this person's pulling and also grounded, pulled in. Okay. And this person pulls with 600 newtons of force. What's the spring scale read? 600 newtons. And what's the tree pulling with? Is the tree pulling with anything on this side?
Yeah, 600.
600 newtons. Yeah, so everything's still 600 newtons. Yeah, 600. 600 across the board. All right, let's see. Who won? Who won Kahoot? Oh, with the bronze, Cole. With the silver, Spencer. And the gold, Anna. Kahoot. Kahoot. All right. Oh, good. We got some time. So let's knock out some puzzles here. All right, so I think we did all the ones on the front, except 22, but that was the same as 21, just a little bit different numbers. So move on here. Okay. Right, so number 48. Okay, 48 is the next one here. During an experiment in physics class, a student places a large block on a plank. The student raises one end of the plank to form an incline until just before the block starts to slide down.
I thought we didn't finish 46.
Oh, did we not?
I don't believe so.
Oh, you're right. Yeah, sorry, I forgot about that. Okay, yeah, let's do it. Let's do 46 then. Okay. A dog is pulling an empty sled attached to a harness parallel to the ground, snow. The sled is moving at constant velocity. Guys, whenever you see constant velocity in physics, what do you know about the net force? Zero. Yeah, zero net force. Okay, because constant velocity, isn't there no acceleration? And according to Newton's second law of motion, if there's no acceleration, there must be no net force. Now, there can be individual forces, but they should all zero out. So 0, 0. Right? The mass of the sled is 1.2 kilograms. They said the coefficient of static friction, but I said change that to kinetic friction. It's got to be a typo if it's like sliding at some velocity. Okay, so we'll call it coefficient of kinetic friction is 0.2. Determine the harness tension. Okay, well, we got to draw this out. You have to draw this out a little bit. Get this. Right, so we've got dog pulling a sled, number 46. All right, sled. All right, let's get a dog here. Yeah. All right, and harness, just like that. All right, mass of the sled is 1.2. Okay, so mass of the sled is 1.2 kilograms. Okay. And the coefficient of kinetic friction is zero point 0.2. Okay. Oh, okay, side thought here. Okay. Zero point 0.2, what is that as a fraction? That's 1 over what? 1 over 5. Ah, okay. So, and you guys know what that means. It means the friction force is 1/5 of the normal force. Isn't that what that means? Okay. Oh, you guys are copying that. Gonna dig out these posters, right? So I'm thinking it probably has something to do with this right here, right? Right. Right. So this could be the sled dog. Oh, actually, you know, this is pretty much it, isn't it? Because guys, constant velocity. That means that the pulling force is balanced out by the friction force. Okay, so this is it, right? Right. So let's do a free body diagram on the sled right here. Free body diagram. Right. So, guys, what is the weight of this sled? What's the weight?
1.2?
Okay,
12.
yeah, there you go, 12 newtons. 12 newtons. Right. Because you guys know that gravity field is about 10 meters per second squared, we usually round it. Okay. So 1.2 kilograms mass times 10, so 12. You guys hear that? You guys, if the weight is 12 newtons and we're on level ground, what's the support force from the ground equal to? Yeah, also 12 newtons. And you know that because the forces have to sum to zero in the vertical direction. Is that true? Right, guys good? Now, what about this detail right here? Oh, you know the coefficient of kinetic friction is zero point 0.2. We just found the normal force. It's 12 newtons. So what's the friction force equal to? Okay. Coefficient of friction times normal force. So where the coefficient of friction goes, I should put zero point 0.2, or 1 over 5 if you like. Where the normal force goes, I should put 12 newtons. Right? Is that 2.4, I think? 2.4 newtons? Is that right? Right. And if I'm drawing my picture to scale, I should draw this backward acting friction force as 1/5 of the normal force, because that's what the coefficient of friction says. Okay. So this friction force we just found is equal to 2.4 newtons. Okay. That's I should use a different ink color. Okay. You guys know what I'm talking about. This one right here. Right. This 12 newtons applies to that normal force, and this 12 newtons applies to the weight. Okay. Right. But I'm missing a force because this shows the sled maybe slowing down, or at least it would be changing its motion. Because constant velocity, I need what else? This tension force right here. This tension. Like that's the question, isn't it? Okay. So what's the tension pulling forward? And since it's constant velocity, what do you know is the tension force equal to?
2.4.
2.4 newtons. Yeah, that's it. That's the answer. Okay. Yeah. So the conditions to solve this were, and I didn't write these down yet, but some of the forces in the y direction goes to 0 newtons. That's how you know the normal force matches the weight. And then some of the forces in the x direction goes to 0 newtons because of constant velocity. And that's how you know the tension in the harness ropes has to match the friction force. Okay. That guys good? And 46. Check it out. Guys go to 46. Right. Now, 48. We're looking at this block on a plank. The student was lifting one end of the plank to make an incline. Hey, I think you guys just did that a few days ago, right? You guys had like an incline. I think I have one incline poster somewhere around here. Okay, but you guys remember this right here? So I'm already thinking in terms of this. Okay, some about an incline, which you guys had a lab on. The block experiences a force of 26 newtons parallel to the incline and 40 newtons, or sorry, 42 newtons perpendicular to the incline. I think they're talking about, well, you guys be thinking about that. What's the coefficient of static friction? So the block stays at rest. Right? And it stays at rest. Isn't at rest one type of equilibrium? Right? It's either sliding at constant velocity or staying at rest. Either one, you get the same free body diagram, like I said. Right. So if I draw that out, like that. Okay. Let's see if you guys can draw this. Okay, put a block on an incline. Let's say block is at rest. See, this was number 48. 48. Okay. I want to see if you guys can draw the whole free body diagram because I just showed you guys my poster version. Give you guys a hint. Has something to do with this rotated Cartesian axis system. Some of the forces might be aligned to that system. They say I just dashed off, like sort of a rotated XY axis. Um, okay. Okay. So ignore the question for a moment, other than this is at rest. So this is at rest. Okay. Because what's one force acting on this block?
Gravity.
Yeah, it's weight. Okay. And which way does weight pull? Yeah, straight down. So that's mg. Okay. Now they didn't actually tell us the mass or the weight of the block. I think we might be able to figure it out. That well, no. Okay. What's another force? True, friction.
Or normal force.
And also normal force. Yeah, both of those are true. There's a normal force that goes kind of this way, probably about that long. There's a friction force that goes this way, probably about that long or so. Something like that. Okay. Okay. I'll label this normal force and friction force. Okay. And I know to draw them approximately those lengths, I think it's pretty close because see these two forces we just drew are aligned with the system. Is that true? Aligned with the system. Okay. But this weight is not. Like if I rotate this whole thing, you see the weight looks like a diagonal. So I can split this into components. Say, well, that weight is partially pushing the block straight into the incline, and it's partially trying to drag it parallel to the incline down to the left. True. You guys have rulers within reach, so you guys can make nice straight lines in your notes. Or you guys mentioned turn this in. Okay. So see what I'm doing is I'm replacing this weight vector, which is like the true force vector, in terms of these two components that conspire to create it, sort of. Okay. And whatever this angle theta is that this angle theta, same theta? So this would be your mg, what, sine or cosine over here? Cosine, because it's adjacent to the theta. And this one is your sine. Yeah, mg sine theta. Okay. Okay. Now let's basic setup. I haven't even put any numbers in yet. Okay. Although, oh yeah, here's what else I want to mention. Okay. See how I see it that the normal force cancels out the mg cosine theta? Okay, that's how I need to make it about that long. And also, see how the friction force exactly cancels out the mg sine theta? It's like same magnitude. Okay. Because at rest would be equilibrium. Right. So what does your book actually say here? It says 26 newtons parallel to the incline. So I think what they're trying to get at, because if they say 26 newtons parallel to the incline, what force do you think they're talking about? Probably the symmetry sine theta, right? Equals 26 newtons. Okay. And or I see this friction is also 26 parallel to the incline. So wouldn't this also have to be 26 newtons? Okay. So this is 26 and this is also 26. But the net force has to be 0 because the block is at rest. Okay. So 26 to the right, 26 to the left. Plus we got 42 newtons perpendicular to the incline. They're probably talking about this normal force, isn't that true? So I'll go ahead and label that 42 newtons. Okay. And for that matter, wouldn't mg cosine theta also come out to 42 newtons? That would also be true, right? Right. Is that? Okay. Ooh, there's actually quite a few good questions you could ask about this. Now, the target question we'll answer first, which is what's the coefficient of static friction? So the block stays right. Now, this is like just barely at the breaking point. Like if this angle increased any more, the block would break friction and slide. That's how, find coefficient of static friction. I can say equals. I don't have to do anything about inequality. I can just say plain equals for this particular scenario. First, say just to the breaking point. Isn't that friction force compared to normal force? Right. Guess you can just pop in those numbers right there to get the answer. Done. Okay. So coefficient of static friction. Let's see. Looking at 26 newtons compared to 42 newtons. Right. So what is that? I'm looking at 0.619. I'll call it 0.62. Right, there you go. Well, that looks fairly reasonable, I think, right? Fairly reasonable. Because here, here's some actual experimental values that are like commonly known. Something like that. Yeah, it looks kind of in the ballpark of those right there. Okay. All right. What else I'm kind of curious to know that we can't figure out is what is the weight of the block and then what's the mass of the block? And also, what's this angle? We can figure out all those things. Okay. So, guys, how do you figure out the weight of the block? Back. Pythagorean theorem. Look at that. Is that a nice right triangle right there? Got the two legs. So let's do square root of 42 squared plus 26 squared. That should tell me this would be the hypotenuse, wouldn't it? Is it? That comes out to 49.4 newtons. Okay. And guys, once you know the weight of the block, how do you get the mass? Yeah, divide by 10 meters per second squared. So would that be like 4.9 something kilograms? Probably somewhere in there. Right? Because mass to weight on Earth, you could just multiply or divide by 10 meters per square, depending on which way you're going. Okay. And finally, I wonder what is that angle theta? Okay. Oh, well, isn't this theta equal to this theta? And if you look at these components right here, guys, the two legs of a right triangle, do these have a sine, cosine, or tangent relationship with each other? That's tangent, right? So I can do inverse tan, opposite, over adjacent. This is just one way to get it. So inverse tan. Well, you guys are catching up to that and put that in. I do have a poster this reminds me of that's very similar to that. It's yeah. Here you go. Okay. All right. So what is this? Looking at 31.8 degrees. 31.8 degrees right there. About 32 degrees. Okay. You guys remember during your lab, you were saying what's the angle that it would slide down at constant velocity? And constant velocity is also an example of equilibrium, so it has the same looking free body diagram, but it's not static friction, it's kinetic friction. Ah, you guys remember that right there? Tan theta? And that's kind of what we just did in reverse. Same thing. You guys good? Good. All right, let's do one more today. One more.
So,
Oh,
can
yeah.
you answer what tan was?
All they asked for was the coefficient of friction, so 0.62. Okay, so everything else was just additional questions. Yeah. All right, so knock out that one point. All right, last one I want to do with you guys is 74. You guys see this Atwood looking setup? So you're designing another dolly sandbag system. Okay, I guess you do a lot of these apparently for a different actor in the performance. The mass of the dolly and actor combined is 76 kilograms. Okay, see, here's the dolly, here's the actor, they're all together on wheels. Hey, you guys did a lab that looks a lot like this. Right, with that part and the whole thing. The mass of the sandbag hanging down right here is 18 kilograms. Now that's a mass. Here. The coefficient of kinetic friction between the dolly and the stage floor is 0.2. Okay, so there's a little bit of friction here also. What's the resulting acceleration? Okay. All right, so I think if I keep a good pace, I might be able to fit this before the end of class here. Okay, I think the best way to approach this is what's called a whole system approach. Okay, so I'll have the weight of the sandbag right here, providing the main external force, call it mg. Okay. Now the other external force that matters is the friction force. So you need to consider that too. The low wheels here, dolly, actor, whole deal. Like that. Okay. And then pulley and straight down there. Okay. So there's the setup. Okay. So guys, if the mass of the sandbag was 18 kilograms, this mass equals 18 kg. Okay. Then what is this weight equal to? About 180 newtons. Is that right? Right, guess that? Okay, because 18 times 10. Okay, and then they told you the massive, well, this whole system up here, dolly and actor, is 76 kilograms, 76 kg, that equals. Okay. So, guys, what's this combined weight up here? 760 newtons. Okay. Therefore, what's the normal force? 760 newtons. Okay. And then, isn't friction force equal to coefficient of friction times the normal force? And the coefficient of friction was given as 0.2. Normal force we just found is 760. Okay. So guess how I can find out the friction force? 0.2. I know I'm doing this kind of fast, but okay. If you're super curious about this one, then I'm recording the video, so I'll post this. All 150, right? And that's gonna resist the motion. So I know to draw that backwards. So because friction force is 152 newtons. Okay. So the forces that matter, I'll circle them. There are only two. It's this one here, the weight of the sandbag saying, let's pull this whole thing down clockwise. And this friction force saying, no, let's hold back, let's resist that counterclockwise sort of. That's everything that matters. Everything else cancels out. The tension's internal, the normal force and weight up here cancel out. So net force is 180 newtons minus 152 newtons. Do we grab that? Is that 28, I think? Is that 28 newtons? Okay. And then the question was acceleration. Guys, if you know net force and you know total mass, can you divide those two? You get the acceleration? Okay. So here, I'll just here. So the net force is 28 newtons, of course. The total mass, well, I got this 76 kilograms here. Plus, remember this bag itself was also 18 kilograms. And all that inertia has to be new, so I have to add all that together. So 28 over 76 plus 18. I'm looking at 0.2978. I'll call it 0.30. And that's meters per second squared. Yeah, okay, so I did that faster than I like to, but yeah, at least we beat the bell, and you guys can get a good look. Oh, I need to get you guys your quiz. Okay, so before you walk out of class today, let me put the quiz in your hands, and that'll be due on Monday, so plenty of time.